This conference will now be recorded.
Back in 1977. So I've been in the railway industry quite a long time, and as part of that I worked for a track renewals company, and I was an infrastructure manager for London, Tilbury and Southend. So I have some knowledge of track, although most of my time has been involved in signalling, with little sojourns off to computer systems and developing HS1 section 2. So my talk is about ETCS, European Train Control System, and it's often suggested that what we're doing is putting the traffic lights into the cab, or signals if you prefer. So I think if we look back at the early days of signalling, we have to admit that either the drivers were very, very clever, or we were very lucky. If you were a driver faced with the signal array that you can see on the screen, would you be able to work out which of those signals applied to you and to know whether it is safe to move? I think that it's the middle bank of 4 red and yellow signals are the ones that apply to the driver of the train in this picture, but I'm not sure. And part of that confusion led to many accidents and a drive to actually put the signals into the cab. As far back as the early 1900s, a number of trials were taking place. Most of those just indicated whether the next signal was at danger or not, and some of them only applied to the distant signal. Some of the systems, like AWS and the Great Western ATC system, were linked to an automatic brake command if the driver didn't respond. A little bit later, there was an experiment where all of the aspects of a colour light signal were repeated into the cab. Part of the problem was that a driver would see a signal and then, having passed it, would forget what that signal had been displaying. So the experiment was to repeat the signal and keep it available to the driver. However, it didn't work very well. It was quite complicated and it was soon dropped. And in fact, none of the early experiments lasted very long. The only one that survived was AWS, Automatic Warning System. And since then, we have added in the train protection and warning system to give some extra protection if a driver fails to obey the aspects and the speed profile. Over in Europe, there were a wide range of signalling systems. Each country, Germany, Holland, France, Spain, had many signalling systems within their country. And it wasn't possible for trains to travel across the national borders without either putting a lot of equipment onto the trains or changing locomotives at the border. And even within some of the countries, trains were restricted to certain routes. So that led to a desire to have a system where multiple suppliers could supply a system that would work across Europe and we could mix and match, aiming for the plug and play. So ETCS stands for the European Train Control System. It's part of a wider system called ERTMS, European Railways Traffic Management System. But the ETCS is the signalling element. It is what supervises the train movements and provides the information to the driver. The key objectives of the system were to provide standardization. This was to get away from the problem of having multiple systems across multiple countries. And if any of you were involved in things like the Eurostar project, the early Eurostar, half of the leading locomotive was filled with different signalling systems, and there was not actually room to fit all the antennas under the first locomotive, and some of the equipment had to be fitted under the first coach behind the first loco. So there was an aim to have a standardized signalling system. And that all fits in with the European objectives of opening up markets through the free movement of people and trade. And the railways got a lot of finance from the European Union in order to develop systems and to implement an interoperable system. It was also recognised that safety was an issue across all railways in Europe. The safety standards for most of the railways is very high, much higher than road and other forms of transport, and yet there was still room for improvement. And some of the areas that were being experienced across Europe were drivers failing to stick to speeds and failing to stop at red signals, things that we're very familiar with in the UK. There was also a key aim of improving capacity on the railway network. One of the problems with the type of signalling you'll be familiar with on the UK network is that the signals are placed at fixed intervals, designed to allow the fastest train to stop from the first cautionary aspect, normally a double yellow, to the red. If you have trains that are travelling slower, that means that you are not using the capacity as well as you could. So there was an opportunity to change the length of those sections, to have more sections, and also to look at having systems where the movement authority for the train was based on the back of the train in front. And as the train in front moves, so the train behind can move further, something that's called moving block. And the last key objective was to reduce cost. It was recognized that supporting multiple safety systems, multiple signaling systems was expensive. And so by having standardized products that could come from multiple suppliers, the aim was to reduce the cost. That appears to be becoming true for projects going forward, but the early implementations have not actually shown the cost benefits that were hoped for. Part of the challenge is that every train operating on an ETCS line needs to have ETCS equipment on board. And if any of you have looked at the variety of trains that we have, then you'll know that they all are different. Trying to fit the equipment onto a locomotive can be a challenge. Where do we put the various computers that are needed? Is there a power supply? Where do we put in the equipment into the driver's cab? And that ends up with typically the first fitment of a type of train costing around £1 million, and the costs then reduce to £200,000 to £300,000 for subsequent vehicles. If you build it into the train when it's new, it is a lot cheaper, obviously. But one problem that we've encountered with fitting trains is if you take an older type of train, it may have been owned or operated by several companies in its life, each of whom will have made alterations. So you might think you are having a standard Class 66 locomotive, but you may find that actually they are all slightly different because each of the owners has added extra systems. So what are we trying to do? Well, we're trying to supervise the safe movement of the trains. And that means that we need to supervise two things: how far the train can travel and what speed can it travel at. TPWS, which we have introduced on the UK network, is quite good at managing the distance to travel. if a driver fails to respond to the cautionary aspects and approaches a red signal without braking, and that red signal protects a significant hazard, then the TPWS will intervene to apply the brakes. And we will, with a high certainty, stop the train before it reaches a hazardous location. However, TPWS is not good at supervising the speed of trains. And we know that it is not uncommon for trains to exceed the permissible speed, or more importantly, emergency or temporary speeds. And for those of you in Network Rail or in supporting companies, you'll no doubt be aware of instances where trains have travelled over broken rails at line speed, even though there was meant to be an ESR in place. So that is one of the functions of ETCS. The information which is transmitted to the train is a movement authority. And this is the term used within the ETCS standards. And the movement authority is the authorized distance that the train can travel. Associated with the movement authority is a speed profile or set of speed profiles. And these are the authorized speeds for different types of train. ETCS allows a lot of differential speeds to be transmitted if we wish to. We can transmit speeds based on the ability of the train to travel around curves, its tolerance of a cant deficiency. We can transmit speeds based on axle loads, and we can transmit some speeds based on the braking style of the train, whether it's got a freight or a passenger brake setting. We also need to tell the train the gradient profile. If you're going to calculate how far it takes to brake, you need to know what gradient you'll be travelling on in the area of braking. Drivers today use their route knowledge, both to know the permissible speeds, where signals are, but also to know how the line is graded and where they need to brake earlier or where they can brake later. Drivers actually do an amazing job, and I have nothing but respect for the amount of information they can store in their heads and process to drive a train safely and comfortably at most occasions. The result of this information sent to the driver is displayed on something called the DMI, the Driver Machine Interface. And it's the most familiar part of an ETCS system. On the screen, you'll see there is a speedometer. It's often called the circular speed gauge. The speeds are always displayed in kilometers per hour in a compliant ETCS system. However, because we in the UK consider ourselves to be special, we have got what is known as a special case, allowing us to display speeds in miles per hour as an alternative. You'll see on the speedometer that the needle has in the center the current speed, 67 kilometers per hour, and it points to the dial. The dial is currently showing in yellow. Yellow means that the driver needs to be reacting to an approaching stopping location or speed reduction. And the target for this is to reduce to 0 at a distance of 290 meters, indicated by the countdown on the left-hand side. On the right-hand side of the screen, you'll see what is called the planning area. About 300 meters, or actually 290 meters, you'll see there is a little golf flag with a 0 next to it. That indicates that in 290 meters, the train is required to come to a speed of 0, or in this case, to stop. The grey bar to the left indicates the gradient, And in this case, the gradient is rising at 5 parts in 1,000. You can see that the planning area can give information up to 4 kilometers ahead of the train. The train is at the bottom and the look ahead goes up to 4 kilometers. The driver can adjust that distance up to a maximum of 32 kilometers or reduce it down to, I think, 1,000 meters. You'll notice it's logarithmic, so you get a lot of information in the next 500 meters, and as you go further away, you get less information. The driver doesn't really need the conventional route knowledge because most of the information they need is on the screen. I'm now going to show you a short video clip. This is of our Cambrian route in Wales, which runs from Shrewsbury to Aberystwyth and up to Pwllheli. And this is actually a driver driving a train back from Pwllheli towards Dyfi Junction near Machynlleth. Top left, you'll see a picture of the driver and you'll be able to see his actions, and you can see in the middle of his cab there is the DMI. Top right of the picture, you'll see there's a repeat of the DMI just so that you can see a bit more detail, and we've also got a forward-facing camera. Now, I'm afraid the sound doesn't work, so you'll have to put up with me talking over the video. So on this part of the line speed is 90 kilometers per hour, and you can see that the driver is keeping the speed needle just on the 90. If you begin to go over the speed, the system will warn the driver with a beep, 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 beep sound, and the driver can then slow down. And some of the drivers have actually got to the point where they don't look at the screen at all. They merely listen for that sound and use that as their cue to reduce speed. Now, we're now approaching a speed reduction over one of the bridges, and you can see that the dial has gone yellow and it goes down to 25 kilometers per hour, where it goes back to grey. This tells the driver that he needs to reduce speed to 25 kilometers per hour. And in the planning area on the right, you can see there is a notch in the grey bar indicating the changes in speed. The forward-facing camera is a little bit of a telephoto, which means that the pictures are slightly out of sync, but you can now see that the driver has slowed to 25 kilometers per hour to pass over the bridge. And if you consider some of the routes that we ask our drivers to travel on, where there are a lot of speed changes, having a system that supervises all of those changes and can supervise them for your particular train means that you have got less route knowledge and less opportunity for error. ETCS is all about supervising for safety. If you attempt to drive over the speed limit, you initially get a warning. The color of the DMI curves changes. It changes to orange as a warning indication. And if you continue to drive over the speed, the brakes will be automatically applied to bring the train back within the permissible speed curve. If you're approaching a reduction in speed or an end of authority, the equivalent of a red signal, then the braking will be supervised. And braking is supervised against the service brake, which is the normal brake that the driver would use and has the expected retardation that you would expect from a normal train. But the system also monitors the emergency brake and considers what would happen if the train had to apply the emergency brake. And that sense, it is a guaranteed brake rate. and it is used to supervise safety hazards. The service brake of a multiple unit or modern passenger train is typically in the order of 9 to 12% of G, or gravity. So that is quite a good brake. A pendolino, for those of you who are familiar with it, can achieve about 15% of G. And if you've been on one which has stopped in a hurry, you'll know that it is quite a sharp brake rate. However, the emergency brake makes a number of assumptions. It assumes that the driver is not trying to brake, so the first thing it'll have to do is to cut the traction. It then assumes that all of the rheostatic or regenerative brakes are not available. We're now down to a straight air brake. It also makes some assumptions that not all of the brakes are working perfectly, and that means that the emergency brake rate is calculated somewhere around 6 or 7% of G. That means as signal engineers, when we design the ETCS trackside, we need to be careful to tell the train where it is expected to stop, which will allow the driver to use the service brake and to brake later, and where the hazards are beyond the expected stopping location, because the emergency brake is what will be used to supervise those. If we don't separate them by far enough, then the train will be supervising the hazard beyond the end of authority and making the driver brake earlier than we want. If a driver does pass an end of authority that's stored on board, the train will trip. Tripping means that the emergency brake is applied and the train is brought to a stand. Before the driver continues, they have to acknowledge the trip, and they also have to go and get permission from the signaller. All of this supervision is often thought to cause a loss of performance. And in fact, that's common of any automatic train protection system. They are by nature conservative because they are based on a safety criteria. Many of you may be aware that on the Great Western Main Line, we have an automatic train protection system which applies on the fast trains heading from London to Bristol. When that was introduced, the drivers had to adjust their style of driving. They couldn't continue to drive hard towards a red light. They had to brake earlier. Everyone thought that we were losing capacity and performance. But how much performance do we really lose? Well, if we do some calculations, from 100 miles per hour at 12% G, it takes about 1 kilometer to stop. And the supervised ATP braking of 8% requires 1,500 meters. If, however, you work out the difference in time that it takes to travel the 1,500 meters, either braking the whole way or traveling at line speed and then braking later, the difference is actually 10 seconds of journey time. So it is not very much. But perception is that you are braking a lot earlier and therefore you must be losing a lot of time. Perception is a wonderful thing. So let's get back to having a look at what the driver sees in the cab. Here our driver is driving along the line and the speed is 120 kilometers per hour. And we can see that in the we're approaching a place where we need to reduce speed, and again to 25 kilometers per hour. When the yellow appears, the driver got a little warning, a beep, 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 beep. And we can see in the planning area there is a notch in the grey curve indicating the reduction in speed. Now, one thing that ETCS doesn't provide for the driver is any indication of where the stations are. And the diagram top right is the signaller's display showing that we're approaching Welshpool. The driver is slowing speed for the turnout into the platform, which is rated for 25 kilometers per hour. And the driver is reduced speed. And we can see in the planning area that we can go through the junction at 25 kilometers an hour, and then we'll enter the platform where we can accelerate again before needing to stop at the far end of the platform. So having cleared the points and the back of the train having gone through the points, then we are able to move into the platform, and we could, if we wished, accelerate to 50 kilometers per hour. However, we do of course need to stop in 200 meters. Now, the reason that the display has gone orange is that there was an early bug in the computer systems used on board on the Cambrian route. This video was taken very early in the launch of the trains. And the orange is denoting that the system thinks that the driver is going faster than they should, even though actually they are able to go as far as the marker board, the yellow arrow on a blue background on the left ahead. Once in the station, the driver will undertake station duties, and you can now see from the planning area that the signaller has set the forward route, and there is now information in the planning area for the next 4 kilometers, and the driver can accelerate up to 80 kilometers per hour. One of the things we learnt very early on was that getting the information right that was put into the system, and then making sure the information displayed to the driver was correct, was very important. And this is where we come to needing some help from you as track engineers. How fast can a train travel on any particular track? Well, things that could affect that are the capability of your track, its curvature, underlying structures, electrification systems, and of course, with conventional signaling, the spacing of the signals and level crossing times affects how fast a train is allowed to travel. So what is your track capable of? And the sort of question that I as a ETCS signal engineer would be asking you is, if I tell you I've got a given type and weight of train, how fast would you allow me to allow it to travel over straight track, a particular type? Could be bullhead, flat bottom, UIC 60, it could be fast clips, Pandrel E's, whatever's. If you know what type of track you have, can you tell me how fast different types of train could travel? And rather than me just saying, I want you to all trains up to RA5 to travel on this route at a certain speed, I'm interested in how fast could an RA1, an RA2, an RA3, an RA4, and an RA5, because ETCS allows me to send a different speed for each of those. Can you tell me for each of the curves what is the cant, and actually I also need to know the radius of each of those curves? Because if I have something like a Pendolino or a Super Voyager, it can travel round those curves faster than a conventional passenger train and still be comfortable for the passengers. A passenger train may be able to travel around curves with a greater cant deficiency than a freight train. ETCS again allows us to transmit different speeds and allows the train, knowing what cant efficiency it can tolerate, to choose the right speed for that part of the track. And if I do allow trains to go round the curves faster because they're a pendolino or something similar, what speed could the all-track system actually support? So I could make a really heavy freight train that tilts, and it would then be okay to run that round curves with a high cant efficiency. But because it is heavy, it is going to put a lot of stresses into your track system. What might be the result? And so rather than us asking, is it okay on this track if we run trains at a certain speed? I'm now saying, you've got the track. You tell me how fast each different type of train could travel, because I have no other constraints on it, and we can begin to get performance improvements. And these questions are quite hard to answer. So what about our maintenance and track staff? Oop, apologies. Where have I gone? Click the wrong button. I do apologize. We can actually tailor our speed profile to match your maintenance regimes. How many locations have you got where you have a 100-mile-per-hour line, which then approaches a station area and the speed drops to 40? What maintenance regime do you apply for the bit of track on the approach to that 40 where you know that no trains will ever be able to travel at 100 miles per hour because they will always be braking for the 40? If you want to apply a different maintenance regime, and that is only, say, applicable for up to 60 miles per hour, with ETCS, we can actually put a speed profile that will enforce that early reduction in speed. Another area where we can help is with temporary speed restrictions and emergency speed restrictions. These can be programmed into the ETCS trackside and transmitted to every train. That means there's no need to go out in the rain or snow to put up speed boards. No need to take out those temporary AWS magnets. No need to go out and replace the temporary AWS magnets when they've fallen off. So we can reduce the workload on our colleagues on the track. However, we're now putting all of the information the driver needs into the cab. And one concern is that the driver will drive with their heads down, looking at the computer screen. Today, we hope they will be looking out of the window and they will sound their horn if they see our colleagues out on the track. So is the change in the driver's behavior going to affect the safety of our workers on the line side? Experience is showing us that actually the drivers tend to drive looking out the window and they glance at the DMI in the same way that you glance at the speedometer in your car as you're driving down the motorway. One thing that ETCS does is to take away the line side signals. That could be an advantage because then can't give staff on the track a false sense of security. If you see a red signal, then you'll assume there is no train coming or that it will not pass that point. And if the signal changes, you may think a train is coming. You can't be sure what information they're telling you. However, taking them away means that we haven't got the same reference locations. If you need to go out and work on the track and you need to block the line with the signaller, a signal identity is a very convenient piece of information to share between the staff on site and the signaller. And of course, we're going to stick more equipment in the track. And one of the things we'll do is to fit passive transmitters called balises into the forefoot. Those of you who've been in areas like Cambrian or the Thameslink route will know that these are yellow paving slab-like items, typically in pairs. And rather like TPWS grids, we as signal engineers will get really annoyed when you take them out, throw them on the scrap train, and we have to go and rescue them later. Just like TPWS grids, we also need to get them back in the right position and in the right order. So we have to work better together. But again, they are an annoyance for people who are trying to maintain the track because they are another obstruction. Now, ETCS does not just replace the signals. Some people immediately think that the movement authority is just the replacement for the aspect on the signal. But aspects don't mean the same thing to every train. They certainly don't mean the same speed of travel. If you're on a passenger train on certain routes, you may be able to travel at line speed until you can see the single yellow instead of braking from the double yellow. A freight train, however, may need to start braking as soon as the driver spots the double yellow in the distance. And there are locations where our drivers are very cautious because they know that if they encounter a cautionary aspect, they will struggle to stop their train in time for the red. Signals also have route indicators. ETCS has no route information for the driver. That means that our signalers need to get the route right every time, since the driver will not have the ability to challenge it until too late. And driving style is going to have to change to account for station stops. Drivers currently use signals and other line-side features to know when to start braking for stations, but many of those will disappear with ETCS. And ETCS also introduces unexpected consequences. It is a change to the way the driver and signaler and other train staff work, and sometimes they can then be trapped into making a mistake. So let us go to Aberystwyth. And here a train has arrived at Aberystwyth and the driver has gone to the other end of the train and is now ready to start back towards Shrewsbury. And as the video starts, we're going to see an indications appearing on the DMI, which is a copy of where the driver is entering data about the train. So the driver is entering the train running number or the head code and confirming what type of train it is. And you can see how quickly they can enter all the data. The system is connected up to the ETCS trackside by radio, and when the driver is ready, they will press start. And because the system is unsure whether there's any train ahead, they're starting in something called on-site mode, where the driver is expected to look out the front of the cab and make sure the line is clear. Now, the unexpected consequence at Aberystwyth, quite early on in the implementation of the ETCS, was that before the train departs, the driver or guard has to press a plunger on the platform. And that plunger affects the operation of one of the level crossings, which we'll see in a few moments. One day, the train manager pressed the plunger, but the signaler had not set the route. And so the driver was unable to get a movement authority. And after many conversations with the signaler, he ended up resetting the train and starting again. And because of that, the speed profile was different for the train leaving the platform. And one of the things that drivers regularly do at an early part of a journey is to do a running brake test. And to do that, they need to get up to about 40 kilometers an hour. As you can see on the DMI, the train is now authorized to travel up to 90 kilometers an hour and has got a movement authority going several kilometers. But on this particular occasion, because the driver had reset the system, they couldn't get up to 40 kilometers per hour until they were round this corner. And the driver concentrated on doing their running brake test. Now, around the corner is an automatic open crossing, and the system is telling the driver that they shouldn't go above 65 kilometers per hour or thereabouts. And you can see the crossing ahead. Now, the unintended consequence of ETCS was that because they had had this problem, the driver was now concentrating on the speedometer and had his head down rather than head up, and hence failed to observe the flashing red light. And as you can see, normal operation, the trains actually get quite close to the crossing before the crossing begins to close. And you can now see the barriers coming down and the flashing white light working. At this time, ETCS did not supervise the train going across the crossing. It was up to the driver to look for that flashing white light for permission to proceed. But in the instance where the driver was distracted because the starting process had been changed, they failed to observe the red light and went across the crossing with the barriers in the air. So ETCS is something where we need to be well aware of how the system will interact with the driver and with other staff, including the P-Way staff. So what's the future for ETCS? Well, one area that Network Rail are working with European partners on is the development of Level 3. Level 3 removes the need for train detection systems, axle counters or track circuits. Each train reports its position continually and the position of the back of the train, and that has to be done in a safe manner. That means that each train can be authorized to move as far as the back of the train ahead, something called moving block. Level 3 can be configured in a number of different ways, and we're working with ProRail from the Netherlands and as part of a European project called Shift to Rail on developing the technical and operational rules for using Level 3. Another opportunity that ETCS gives is automatic train operation. Trains through the Thameslink core are regularly operating with ETCS and automatic train operation. Network Rail are leading the work stream in Europe to develop a harmonized automatic train operation system. The Thameslink system is one developed specifically by Siemens. An automatic train operation and the potential of Level 3 in one of its variants are being considered for HS2. So ETCS offers great opportunities for the railway system in terms of safety and performance. And to achieve those goals, we need to be prepared to change. And one of the challenges I have in my role, which is to develop what's called a reference design, is to consider how we use the items in the ETCS toolbox, how we decide how to configure them, what operational rules need to change, what training needs to be put in place. And for many of these areas, we have to forget the signalling that we're all familiar with. We have to forget how the railway works. If we just try and make ETCS fit the current railway, as we have done for the Great Western, where we've added ETCS to the line-side signals for the Heathrow line, then you end up with a very expensive implementation with no operational or performance benefit. In fact, sometimes the opposite. If we're going to make ETCS work to reduce our implementation costs, improve safety and performance for the future, we have to be prepared to be quite radical. So that's a short introduction to ETCS. I did say to the institution I was quite happy to do the 4-day version of the course that I teach in Europe, but they seem to think that you would just like a 1-hour introduction. So I'll now open up to questions.
Thank you, John. And I found that very, very interesting. I was lucky enough myself to work on the Cambrian project in the very early stages of my career. So I was familiar with a little bit of what you were talking about, but it was good to see it in action in some of the videos. A couple of questions have come through, and I do just want to say to everyone on the call, there's the chat function at the top right hand side of the screen, which is the speech bubble. If you click in there and then type a message with your question in, that will come through to myself and the organisers, and I'll start asking John the questions now. Before I do get to the questions from the chat, I've got a quick question for you, which was in the UK, obviously you talked about Cambrian and Thameslink. Is there any current plans for rolling ETCS out on any other routes at the moment?
Okay, so Great Western, we have got a section of ETCS working in the Heathrow tunnels and coming out towards Acton, and there is a plan to roll that down as far as Paddington, and that development is well underway. In fact, one of my colleagues from my team has just left to support that project. And for East Coast, there is Siemens have been engaged to deploy ETCS from King's Cross to Decoy, which is just south of Doncaster, including some of the branches. That will start with the Northern City lines, the Moorgate branch, and that development work is now underway. It takes a little while before you see very much happening on the ground, but that is happening. Discussions are underway for the Transpennine route upgrade to deploy ETCS there as well. That route, if any of you are familiar with it, is very twisty, and the objectives from the Department of Transport are to increase the speeds or by reducing journey and to reduce journey time. And the line is so twisty that to actually get signal sighting is a challenge. So ETCS would be a solution for that. So those are the ones that are currently sort of well underway in terms of development.
Okay, excellent. The next question comes from Andrew Cooper, and he says that today's driver behaviour will be influenced by the fact that they have the route knowledge and so can work heads up because that's their training. The benefits will come from having little route knowledge, so the need to work heads down, except for to look for markers approaching stations. With trespass and suicides not reducing, can we live with more heads down driving?
Well, I suppose I would say, how many have you got a sat nav in your car? And how much time do you actually spend looking at it? And that's, if you think about that first video I showed with the driver, if you actually looked at him, he never looked down at the screen. He glanced at it from the corner of his eye, but he was looking out the side window, looking at the front, turning and chatting to the inspector in the cab with him. He didn't actually concentrate on the display. And as I said, when we're looking at the video, there are some sound prompts which help. So if you overspeed, you get a warning. If something changes that you need to take account of, you get an alert, a beep beep sound to alert you that there's something that's changed. So we don't think that many drivers will drive heads down. And in fact, I was talking to one of my colleagues from RDG yesterday about this very issue, and he said on the Cambrian that most of the drivers are heads up the whole time. They're looking out the window and they just glance at the DMI, just like you glance at your sat nav or your speedometer. He'd also did touch on route knowledge, and he was talking about the two types of drivers they've got on the Cambrian, the ones who are familiar with the line before ETCS, who know where the speed reductions are, know where things are, and are driving to the historic speed profiles rather than the new ones, because we have changed the speeds, where against new drivers who were unfamiliar with that and drive differently. So it is interesting how people behave, and route knowledge is one of the ones which some operators are really keen on the fact that ETCS would allow a driver to be diverted onto a route they may not be familiar with or may not have up-to-date route knowledge for, and it would still be safe. Others are horrified at the idea that we might allow a driver who has no route knowledge to take a diversionary route. So there's lots of things, and this is where I say we need to really be able to think outside the box. We need to challenge everything, and working with my colleagues from railway undertakings, from GTR, from East Coast, from some of the freight operators, it is interesting how in some areas they are prepared to change everything they do. In other areas, they get incredibly nervous at any change. And if you ask them to rationalize it, it's very hard to get some safety issues. It's just gut feel that that's wrong. So that's interesting.
Okay, thank you for that. I think with a lot of things with the railway, often the human element can become the most interesting and also the most difficult to overcome. So yes, an interesting reply. Next question's from Philip Holden, and he says, it's surprising how little information is included into the ETCS display. No stations, for example. Is the inclusion of this information still in development, or is this an active decision to exclude it?
Okay, so yeah, stations was one of the things which has caused us some grief because we are aware that that is going to be an issue. There is no plan to include stations. ETCS is managed at a European level, and whilst each of the member states, so that includes ourselves in the UK, even post-Brexit, I hasten to add, we are able to make bids for changes. However, the inclusion of station information has not been pursued by any of the railways. And one of the problems is that what stations do you include? Do you include the stations that train is meant to stop at, or every station? So if you think of travelling from Euston to Birmingham New Street, and you're travelling on a Avanti Pendolino, you might stop at Milton Keynes because it's the centre of the universe, and perhaps Coventry, and Birmingham International. But in your journey, you have gone through a whole series of stations, all the suburban stations down to Watford area, the suburban stations on the approach to Birmingham New Street. So if you show all the stations, does that actually help the driver? If any of you get the opportunity to go in the cab of something like a Pendolino or any of the more modern multiple units, you'll find that the train management system often includes driver advisory information. So on a Pendolino, when the driver enters the head code, it loads the timetable and it will tell you that you're due to stop at Milton Keynes, and it will give you a warning when you're about 3 kilometres from Milton Keynes to say you're due to stop at Milton Keynes in 3 kilometres. So ETCS doesn't provide the information, but other systems can. There is a version of ETCS that's being developed as part of the ATO project, which would provide some more information about the timetable to the driver in an advisory form. Whether that's going to be deployed, not sure. Part of the reason for keeping the information sparse on the display is to avoid the driver concentrating on it. Give them what they need and don't clutter it up with lots of extra information. Some information like neutral sections can be included, but again, we've got to think about how much time the driver might be distracted and looking at the display instead of looking out for our colleagues on the track ready to sound the horn.
Okay, thank you for that one. The next question comes from Ian D, How can I find out further information on the mapping system of ETCS?
Okay, right. So ETCS doesn't have a mapping system. It's the first thing to say. Everyone thinks that the trains know where they are. They don't. They're stupid. And if you think about it, it's quite logical that they don't know where they are, because the whole idea is an ETCS train can travel anywhere on any ETCS railway and it'll work. What the train gets is information from the trackside, and that information is based on a common datum. So those yellow balises that we install in the forefoot become the datum point. And any information that the train gets is related to the last of those balises that it read or passed over. So it gets a distance you can travel and a speed profile that you can travel from that last balise group in the forefoot. It has no real knowledge of where it's going, and it doesn't know whether it's going to turn left or turn right. It just knows that it's allowed to travel 3,000 meters from that last balise group, and the speed profile it can apply is whatever it is. So there is actually no mapping system. However, on the track side, we obviously do need to know exactly where everything is, because in order to tell the train how far it can travel and how fast it can travel, having passed one of those balise groups, we need to know where the balise group is relative to all your S&C, relative to speed reductions and anything else. So there is on that side, but that's not that dissimilar to a traditional signalling scheme plan. Although some of our suppliers have tried to imply that we need to measure the railway with an incredible accuracy down to about 10 centimeters, whereas the system actually has so many compensations built into it that it doesn't actually matter if you measure to the nearest 2 or 3 meters. It'll compensate for that. But if Ian wants to get in touch with me afterwards, then I can discuss it further if he wants some more information.
Okay, excellent, thank you. Next question is from Ed Harris. Could any new technology from driverless cars be accommodated?
Well, that's an interesting one, because our colleagues in Germany are looking at driverless automatic train operation as an option, particularly for some of their freight trains. And the key safety issue then is, how do you make sure the line ahead is clear? How do you detect people on the line, or do you make it a no people railway? What about obstructions? And the idea of using LiDAR or video technology on the front of the train in order to be able to detect problems might be something that could be transferable knowledge, yes.
Okay.
We do have to remember, of course, that unlike Richard Branson's statement that drivers have got a steering wheel in the cab, our drivers don't have to steer around things.
Sure. Next question from Steve Featherstone, who can recall working on the Cambrian line around 10 years ago, and just follows on from that to say, is there a risk that by the time we're able to join all the systems together, the early systems will already be obsolete?
Well, the Cambrian system is obsolete, he's right. The specifications have been improved over the years, and the Cambrian was built to a set of specifications which were still at the draft stage, and hence the trains are not compatible with other ETCS implementations that we have deployed. Transport for Wales are in the process of procuring new trains for the Cambrian, and they will be upgraded or have an upgraded version of ETCS on board, the latest version. And as part of that, we will have to do some tweaks to the ETCS trackside on Cambrian so that it works better with them. It's a little bit like compatibility on your computer. Your latest version of Word can read the old version of Word files, but the old version of Word couldn't read the new version of Word files. So there's what's called forward compatibility. So yeah, Steve's dead right. What we have installed is already obsolete. The system on Thameslink was to a later set of specifications, but they were also draft. Well, they'd been issued, but then they were superseded. So Thameslink is not quite to any of the current specifications. The installation on Great Western is to another version of the specs, and the East Coast will be to another version. So that is a big challenge both for the train operators and particularly our freight colleagues who are busy fitting all the freight locomotives, but also to us who maintain the signalling.
Okay. Another question now from Andrew Thornton. A lot of information is loaded onto the system, e.g. the gradient profile.
Yeah.
Is this from recent surveys or from some older published information, and how is it kept up to date?
Another little challenge, and it's one of the reasons that our asset information people are looking at moving towards a BIMS type system and maintaining the BIMS data. Gradient profiles, well, that's an interesting one. Where do you find a gradient profile that's accurate? You go back to Mr. Brunel's original drawings, probably. That is a big challenge, but it's also that as track engineers, you'll know very well that you don't have a rising gradient 1 in 1,000 that suddenly becomes 1 in 400 falling at a point. You actually have a transition from rising to falling over quite a distance. How do you document that? So yes, Andrew, we do need to do quite a lot of surveys. Again, we need to be really aware of how accurate those surveys need to be, and we need to try and make sure we do the survey once and we do it efficiently, and that the information we collect supports all of the uses, not just ETCS, but everything that you as track engineers may wish for, anything that we need for other asset information systems. Let's do it once and do it properly.
Okay. Next question from Alex Baldwin. Does ETCS support the protection of maintenance staff through adjacent line open implementation with a speed restriction?
Yes, I think I remember Alex and I probably had a session at Westwood at one point, talking about how do we protect our staff on trains with ALO, where we were finding a lot of drivers were not obeying the temporary speed restrictions. One of the advantages of ETCS is that the temporary speed restriction is actually input into the ETCS trackside and transmitted to the trains as part of their speed restriction profile. So if we know that ALO is taking place at a location and you put a TSR on the adjacent track, that will be enforced. It will be part of the supervision of the train. And so you won't have a train whizzing past you at 100 miles an hour when you thought you had a 40 mile per hour on beside you. ETCS will actually improve that. And because it's just done in software, I know that's a dangerous thing to say, it also means it's much easier to adjust the limits of it as work progresses, or to make sure that it's placed at the right place for each night's work, particularly where you've got progressive work and there's sort of those horrible dagger speed restrictions that occur. So hopefully we can actually improve the safety of our colleagues working on the track.
Okay, and then the next question from Andy Batters, specifically for on-track machines and infrastructure trains, which may change their configuration, length or weight. How does this affect the train's profile and authority when exiting a possession back onto the ETCS infrastructure?
Oh, good, really good question, because one of the things that ETCS needs is to know the characteristics of the train, how long it is, how good its braking system is. And it's not actually interested in the weight, it's actually interested in how effective the brake is. Now, depending on the type of vehicles, often the brake force or the ability to brake doesn't change very much with changes in weight, because brakes become more effective the heavier the train is, because of the amount of grip you get on the rail. Also, there are some brake regulators which automatically adjust to the loading of the wagons, particularly. So that but yes, collecting the data of a train and allowing the driver to input it accurately is something that we have been tussling with for about 6 or 7 years now. Still don't have total answers, but we are getting a bit closer, and it will mean that the job of the people who inspect the train before it leaves for possession may have to increase a little bit. We may need to provide them with an app on their iPhone or whatever, so that they can record each of the wagons, which will then give the weight and the brake capability of the train. But really good question.
Thanks for that one. I think we'll do a couple more questions, and then I might bring things to a close. So the next one's from Liam Jackson. Are there any examples of successful ETCS level 3 implementation in Europe or further afield?
No, I think is the answer, and that's partly because the specifications are still being worked on. And as I said, my colleagues and myself have been working with our European colleagues for some years in a project called Shift to Rail, where we're trying to develop the next stage of the level 3 specs. It has been trialed, and in controlled environments, like level 3 works really quite well for a metro type railway, you know, an underground or something similar, where you've got very fixed formation trains. They all got the same characteristics. Trying to make it work on a mixed traffic like the West Coast Main Line or the East Coast Main Line, that's much harder, and that's the area that we're still working on. So not around yet. And reading the question from about the DMI information, yes, it could be displayed on a head-up display. That's probably a good idea, but no one's suggested it yet.
Okay, definitely one to take away then. Somebody's come out with a good suggestion there from Anthony Tranter.
Yeah, no, I think that's a good idea.
We'll get to one final one, possibly from Andy Savage, who says he was interested to see and if I've pronounced this wrong, forgive me, clam banan detail, as he investigated previous near miss there when at Rabe. Is there sufficient investment funding from DFT to enable trains to be fitted on routes where there is not a dedicated fleet, as is the case on the Cambrian?
Okay, so what's the government have funded the fitment of freight locomotives via the ORR, paying Network Rail to pay the freight companies. So freight fitment is now underway. They have also funded the development of the design for first-in-class fitment of most of the passenger fleet, and that is underway as well. And the franchise arrangements will be to fit trains. The DFT rule was that all new trains being purchased would come with ETCS. However, in the manner of all good civil servants, they looked at the fact that it cost an extra £50,000 a train to fit the ETCS, so they decided not to, and now I've got the problem that it's going to cost £200,000 to retrofit it. But that was fine. They saved some money when it mattered. A bit cynical there, sorry. But yeah, the plan is that we will fit the trackside once sufficient trains that operate on the route are fitted with ETCS and are ready to roll, so that any residual fitment is relatively small and therefore can be done economically.
Okay, that's excellent. Thank you. Thank you to everyone for the great questions. Just falls to me now at the end to just say a few thank yous. So firstly, thank you to John I found that a really interesting presentation. As I say, I was lucky enough to work on the Cambrian in the very early stages of my career at its implementation, and it really was nice to see some of it actually up and running and how it works in practice, which I don't think I'd have seen as a track engineer in any other way. So I found that fascinating, and I'm sure from the amount of questions we've got that a lot of the other members have found it very interesting too. We had a peak attendance today of 98 people, which is really, really good. Thank you to everybody who's attended from both sections, both from Milton Keynes and from Birmingham. And indeed to anyone who's joined us from further afield around the country, you're always welcome. And it's nice to have a big attendance to make it worthwhile for the speaker, hopefully. So on that note, thank you all very much. Happy New Year. And I look forward to seeing you again at the next section meeting in March, which the details will follow shortly from Kevin and myself. Thank you.
Thank you.